San Diego Bay, which is adjacent to downtown San Diego, as well as several other municipalities in San Diego County, houses 11,000 acres of marine habitat, with the third largest eelgrass habitat area in California. As such, it is home to a diverse aquatic population that helps sustain various fauna, which use the bay for breeding, rearing young, and migratory respite. Additionally, it is one of California's 5 major ports and serves as an important hub for industry and commerce, such as the international shipping trade of automobiles and other commodities, as well as for recreation, cruise ships, and the U.S. Navy Pacific Fleet. In 2019, the Center for Climate Change Impacts and Adaptation at UCSD embarked upon a collaboration with San Diego Gas and Electric, the San Diego Airport Authority, and the Port of San Diego to investigate flooding vulnerability along the entire San Diego Bay shoreline. The goals of the project were to generate data and model output to understand water level fluctuations, wave energy, and potential flooding both today and with sea level rise. Moreover, we are investigating the oceanic and atmospheric drivers of extreme water levels in order to characterize shoreline vulnerability in a variety of extreme event scenarios, in an effort to inform effective decision-making for shoreline protection design, adaptation strategies, and flooding mitigation. In addition to the stakeholders previously mentioned, a number of other agencies have been actively involved in the co-production of this project, including the Tijuana National Estuarine Research Reserve, the U.S. Coast Guard, the U.S. Navy, various municipalities around the Bay, and engaged citizens. These groups have all supported and informed the placement of in situ pressure sensors and aided in storm documentation over the past 2 winters. One such event, shown here, highlighted the impacts of elevated non-tidal residual water level, a moderate tidal amplitude, and extreme winds, which drove local wave generation. In this event, a low-pressure system underwent cyclogenesis near the Gulf of Alaska and developed an atmospheric river as it strengthened. The system then propagated southeastward toward California. The following videos were recorded during this event by our collaborators and have been collated as visual references for comparison against our in situ data. As you can see, there are a variety of shoreline types and uses around the bay, which means that not all locations will experience the same magnitude of impacts. In documenting storms such as this one, we are able to catalog the most impactful events and focus our investigative efforts on this variety of storm in our data and model analysis. The in situ observations provide the capacity to validate the numerical model of the bay and characterize important sources of energy. The numerical model we are investigating utilizes the COAST modeling system. At the largest domain shown here, we run the ROMS regional hydrodynamic model and encompass the entire Southern California bight. At the finest domain, we run ROMS coupled to the wave model SWAN. The open ocean boundary conditions are taken from the California State Estimate, which is a data assimilative model, which ingests all of the available observations in the region. The atmospheric forcing comes from the North American mesoscale model, and at the finest domain, the wave model is forced by CDIP's swell model. We also incorporate the observed river flow and get down to resolution representative of scales along the bay. From the model, we can conduct dynamical analysis, extract time series, as well as extract wave spectra to drive phase resolving models in specific locations if desired. From the time series, it is clear that storm conditions are the primary drivers of elevated wave energy and water levels within the bay. In our ongoing work, we are collaborating with the Center for Western Weather and Water Extremes to incorporate high-resolution atmospheric forcing into our ocean model, the need for which has been identified in our initial investigations. This example animation of wind vectors clearly indicates the role of local topography in influencing the wind field around the bay and adjacent coastline. In the future, we would like to utilize probabilistic approaches such as, for example, Tesla to investigate the parameter space that the events documented and analyzed in our study occupy, as well as provide stakeholders with a predictive tool. For further discussion on this work, please contact Mark Merrifield or Angelica Rodriguez at the Center for Climate Change Impacts and Adaptation, UCSD.